We're ready to start. Hello, everyone. Welcome to this new lecture. The topic today is the MAC layer. The MAC layer is the less visible of all the layers because when we do ping, traceroute, we see nothing of the MAC layer. So we will, in the lab, use special tools for that. It's also perhaps the less well understood and the more underground. Fortunately, because it works well, there's not so much we need to know about it, but there are a few interesting things that we will discuss today. So let's start with a historical view of what the MAC layer is. That explains why the layers are organized this way even today. Back in the 70s, when the MAC layer was invented, MAC layer stands for medium access control. Medium means a cable or a radio channel. And the problem was to connect multiple computers. I draw them as PCs. At that time, PCs were hardly existing, so you should rather think of mainframes or huge boxes. Connect them via a shared cable, right? That was a complete revolution. Not everyone was connecting computers in this way at that time. At that time, there was another technology that was used. It was the telephone network. You could connect computers via telephone lines by putting modems. And what the modems were doing at that time, they were translating bits into audio signals, because the only thing that the telephone network could do was to carry audio signals. So in the very old days, you had modems that you could hear what the modem is doing. It was doing something that appears to be noise to us, but I was translating the bits into audio signals that were then translating into electromagnetic signals by the speaker and the microphone of the telephone system. Of course, this is a bit inefficient. Very quickly, people replaced the audio part by putting a direct connection of a physical layer onto the telephone cables using telephone switches. That was the alternative to what we're doing here. The idea here was that when computers talk, they're not like when we call over the telephone, but the traffic is bursty. At least at that time, it was very bursty. Bursty means that when you want to access a file or an object somewhere on a computer, you want it as fast as possible. And then most of the time after that, your computer is doing nothing. That's an image of what we're doing when we browse a server, or when two computers interact together, with the exception of when you do a massive backup from one disk to another, then you need a very long transfer time. But otherwise, most of the time, traffic is bursty. That means traffic comes together over a short period of time. You send a request to a computer, you expect a reply, then you compute. While you're computing, you send nothing. Circuit switching, as in telephone, is not an efficient way of addressing such a need, because in a circuit switch network, you dedicate a circuit from a computer to another, and whether they speak or not, or the physical layer is used entirely. So there's lots of silence, which is not used. So the idea was to do things differently, pull a cable. At that time, there was a coaxial cable, same as the cable TV, that would go from one office to the other through the walls. We had that at the beginning at EPFL in my offices, and connect them together. And the revolutionary idea is, as you see on this picture, there is no central component. You just connect all the systems together. It's fully distributed. Right? That's typical of the protocols that were developed in the 70s, 80s, and 90s even. We will see that when we study routing protocols like OSPF, they're fully distributed. We see that there's a trend today to come to more centralized systems again, because they scale better, but that's also more error-prone. The failures are more difficult, are more dramatic in centralized systems than in fully distributed systems. So that was the job goal that the people who invented Ethernet set to themselves. So what is the problem? So we pull a cable, we connect every computer to the cable. So this box here is simply a derivation. It's a T connector. You physically drill a hole into the insulation of the cable, and then the central copper wire gets connected through this hole, and the coaxial cable has two wires, one that is at the center, another one that's around. And so it's just only physical wiring, those boxes here. So if we do that, we have the problem of what is called interference. The problem is what happens if computer A sends a packet over these wires and at the same time B also does. Then there will be a collision, probably. That's the problem to be solved. Right? So if A and B send something and C wants to see who sent what, then it will just have the superposition of two packets, and probably this will not be easy to decode. That's the problem. So this problem is solved today with different mechanisms. In the physical layer, we know today how to do this, at least with some limited amount of collisions. That is called joint decoding. Even if multiple systems are talking together, there are ways to be able to decode only one of them by using, for example, orthogonal coding mechanisms that will translate the bits into ways that are smart, such that even if two send together and you know exactly whom you want to decode, the other one will appear as noise. At that time, that was not known at all, so this is not done at all in the MAC layer. So the other solution is mutual exclusion. That's a solution that comes from computer science, from the world of distributed systems. That's a problem we have in general at all layers in communication. When you have multiple servers or multiple machines that want to talk, that interact for something, and they have to exchange messages. And then mutual exclusion means that at one point in time, only one of the machines should be able to access something. This is typically what you do in a database system. When you write a record, when you change the value of a record, you have to make sure that you have a semaphore or a lock on this record so that no one else would be writing at the same time. So it's a common problem that we find in computer science everywhere. So, and this is the solution that was done here. We want a mutual exclusion protocol, one that allows only one computer to speak at a time, but we want this to be fully distributed without any central system here. So even in this specific way of solving the problem, there's a wide range of solutions that all exist in the fields today. The first range of solution is deterministic. So this is very similar to what we do in if we use this telephone system to interconnect computers together. This is what is done, for example, in field buses, CAN bus. Those are the low bitrate buses that are used in most of industrial networking and industrial computing today, at least for the, let's say, the low end part. So you have here wires that connect the different machines together, and all the machines are time synchronized, and we agree on time slots when every machine is allowed to speak. So we give a slot to machine A, another time slot to machine B. Cellular telephony of generation 2. So we are now at the 4th and 5th generation is being deployed. The second generation of cellular telephony was using exactly this. So over the wireless channel of a cellular, given by a cellular tower, you had TDM, you had time slots, and a given mobile was instructed which time slot to use via the signaling channel. And once you have acquired, when you place a call, you have a given time slot. This is easy to do, because this is why it's done in low-end and cheap systems, but it's largely inefficient for several reasons. One of them is doesn't handle the burstiness very well. The other one is a more physical layer reason. When you have fixed time slots, you have on-off signals that tend to have a very large bandwidth because you go from full power to zero power. At the time you do this, you have a sudden change, which, if you do the Fourier transform of this, has a wide spectrum, which means it creates a lot of parasites. This is why, in fact, telephones can create on your audio system. If you have a telephone that is using old-style telephony, you will hear, in fact, the change of time slots by interference that goes over the whole spectrum, including the audio frequencies. So this is not very efficient, but it is very easy to do. Our colleagues at XEM did something very efficient that goes in this direction for extremely low power MAC layers. By extremely low power, we mean a device like this one that would be able to run for 1 full year over the battery, over its battery, without having to charge the battery over a full year. So such systems use TDMA because that's very efficient from an energy viewpoint if you're going into the extreme low power. Because if this system is synchronized to send a message, for example, at given time slots that it knows, it can go off power between all the times when its time slot is not given to it. So that maybe a reason for using that. But Ethernet doesn't use that. Then there is a range of solutions that use token ring that are still used in distributed systems today. That were a competitor to Ethernet. So last century, there was a lot of token ring solutions that were deployed. They are more efficient than Ethernet, but evolution does not always favor efficiency. It favors a complex mix of properties, where the idea is you pass a token. When computer A speaks, it needs to grab a token. And then when it's finished speaking, the rule says it can speak for some limited amount of time. Then it sends the token to the next to its neighbor. So you need to wire the system as a ring. And once the system is wired as a ring, the token passes from one neighbor to the other. That solves the burstiness problem very well, because if no neighbor needs to speak, then the neighbor immediately passes the token to the next neighbor and so on. So the idle periods will not be used very much. So if you are alone speaking, you will get the token back and you will be able to speak. But that's very fair in the sense if another system wants to speak, then it will get the token as much as you, and the bandwidth, the bit rate will be shared in a very efficient way. This is used in some distributed systems at the application level. As I said, it's had become obsolete in the physical layer. Now, what is used today is Ethernet, historical Ethernet. As we will see, today's Ethernet does not use an exclusion protocol. We will see why, but it's used in Wi-Fi. So the most widespread use of those ideas are in Wi-Fi. In Wi-Fi in this room, we're all using the same antennas, and there's two here. And when we go to one of the two antennas, then we need this mutual exclusion protocol. So only one of us can send a packet to one antenna at a given point in time. This is also used in power line communication, which is very similar to Ethernet, but uses the electric wires. So many, for example, TV cabling at home use that type of communication, and all the zoo of wireless communication for low power. Sometimes the very low power, like I mentioned, use a combination of this random access and deterministic access for the saving power. So random access is based on very simplistic idea. That's very typical of computer science. In computer science, when you have something complex to do, you don't start with the complex thing first. You first try a very simple solution that works in very simple conditions. And you make sure it works completely in very simple conditions. And then you're so happy because programming is so difficult and it takes so much time and there are so many bugs and you need to know all the interfaces and everything. So once it's done, you think about, now let's solve some of the problems if you want to scale or if you want to have other operating conditions. So that drives the way things are. In some sense, this thing it's different from other sectors where, for example, in the aerospace industry, when you design a plane, you don't do a small planes that flies easily and is 20 centimeters large and you make it bigger. No, that's not the way you do, because there are physical scale effects. If you design an Airbus or a Boeing, you think of it from the beginning as a very big thing and you make small pieces and it takes 10 years to develop, etc. This is not how all those things have emerged. People have not done the internet by saying, I'll do BGP, I'll do OSPF, I'll do this. So this research center, you do BGP. No, all of this has emerged from small things that have organically grown to become bigger and bigger. And this is why we are the way we are today. The very first protocol that goes into this direction is called Aloha. And that's the mother or the father of all protocols of this type. We find it, for example, on the signaling channel of cellular communication. The signaling channel solves the bootstrap problem. When you have a mobile device and you want to connect to a base station somewhere, you are not yet connected. So there is a period where you try to acquire the signal. So the base station does not know you yet. So the base station has not allocated the physical layer resources that are allocated to you when you start using a given base station. So in this approach phase, we use a protocol similar to this or based on this one, which is called Aloha here. Aloha was not developed for the traditional cellular telephony system that we know today. It was based on research done in the 70s in the Hawaiian Islands. So imagine all of those 5 boxes are on different islands. And on each island, you have one computer. At that time, one computer was a big thing. And they want to communicate together. And because they're on islands, pulling cables was not an option. So you wanted to do it via radio signals. And there was a central computer, very typical of that period. That period was that of store and forward, where when you transfer data from A to B, you transfer it to a mainframe, to a central computer that would send it later back. So email consisted in having the local computer here, send the email to this local computer that would analyze the destination and send it back to this one. So there was no IP, if you want. Here, in this system, there were also two frequencies, one for communication from the center to the remote islands, and another one from the remote islands to the center. And since there is a single sender on the, let's call this the downlink channel, on the downlink channel, there is no exclusion problem. There's no collision because there's a single sender. So this central computer knows when it sends a packet to A versus B, so it just can manage its access to the channel. The problem is on the reverse channel. When somebody on island A wants to send a packet and someone else does the same thing at about the same time on island B. Of course, island A and island B cannot communicate directly. If they could talk together and call and say, hey, I'm sending a packet, please don't, okay, that would solve the problem. But you don't want to do that because calling means you have a communication mechanism in place, and that's exactly what we're doing. This protocol is supposed to replace the calling. So the idea is here simplistic. It consists in saying, well, when you have something to send, so this is the algorithm that is done by a sender, a remote here. You send the frame on the channel using whatever physical layer you have at this time. And the protocol specifies that whenever the sender receives a packet, it should send an acknowledgement on the return channel on which there is no collision. So when you send a packet, you wait for the channel. If you receive the acknowledgement, then the protocol is received, if the packet is confirmed, and you're happy, your packet was received. That's exactly the stop and go protocol that we have seen 2 weeks ago. With a variant here, if you time out, then with a stop and go protocol, if you time out, you resend. But here, if we time out, we think, well, there's zillions of reasons that can cause a packet loss. But one important reason could be because there was a collision. There was someone else on another island sending a packet at the same time, and the center was busy decoding that one, or worse, was receiving two, and it just saw too much noise and could not decode anything. In any case, it did not receive my packet. Therefore, my packet was not received, presumably because of a collision. Of course, it might be due to other reasons, like wireless errors. But this, here the assumption is the main cause we want to catch is collision. In that case, what we do, we resend. But if we resend immediately, of course, that would be stupid, because if someone else was sending and they do the same, then we both send again. So we will create a synchronized set of collisions that will simply put us into a deadlock. So what we do is wait for a random time. How this random time is chosen, we can discuss. Essentially, it's we wait for a random time that's drawn from a distribution, a geometric distribution. And with large probability, if there is another one having a collision, the random time will be sufficiently apart from ours, such that when we try again, there will be no collision. So that's what we call an optimistic procedure, which works well if traffic is sporadic. If most of the time there is no collision, if there is once in a while a collision, then you will catch it. Again, this is what is done more or less on the signaling channel when you try to connect over a specific frequency that's dedicated to speaking to the base station. Most of the time, nobody is doing it because you do it only when you approach and try to get connected to that base station. So this is exactly what is done. It's called the Aloha protocol. It's not very efficient. It's very simple. It's been analyzed extensively. The analysis, the design is very simple. The analysis is extremely complicated. So you need Markov chains and interesting stability theorems with Lyapunov drift and all that stuff to show whether it's stable or anything or not. We won't go into that, although it's a fascinating topic, but it's not the one of this course here. The maximum utilization has been proven to be 18%. So if in average the channel is busy more than 18%, then the thing becomes chronically congested. So that works only for very sporadic traffic. If the packet sending is rare enough, then once in a while there is a collision, and the randomness of the backoff will make sure that the collision more or less gets resolved. Except if there's more traffic that is generated, then the probability of collision increases, and when you retransmit, then you increase the apparent traffic so that you have a cascading effect that will bring the system down. So stability requires that the utilization is lower than this magic number. It's not exactly 18%. It's I'm not sure. It's a slightly more complicated number, but that's around 18%. So this is the very basic principles that is used in Ethernet, the very first Ethernet. So people knew of this protocol, so they've done it. But here they said we're not in the same system. First, there is no center. Second, we have a coaxial cable. Coaxial cable is very good for transmission as long as it's not too long. So here the original Ethernet requirement said it can be up to 1 kilometer. So local area network meant here physically 1 kilometer for the cable here. Over a 1 kilometer coaxial cable, we can assume the medium is transitive. Transitive means that any event that's occurring anywhere on the cable can be heard everywhere. So if A sends a packet here, B, that is at the farthest end, will hear it, will see that something is happening. Which is not the case in the previous Aloha, and it's not the case in Wi-Fi. There are what are called hidden terminals. But here, that was the assumption that was made. If we have this assumption, then we can dramatically improve Aloha by listening. This is what we do in this class. In fact, I'm speaking and I'm alone speaking, and I thank you very much for that, because you hear that I'm speaking and therefore you don't speak. Right? So that's exactly the idea that is here. When a node has a packet to send, what do? First, you listen to the channel. You make sure there is no traffic being sent on the channel. And since the medium is transitive, you know that if somebody is sending, you will hear it. So if you listen and nobody is sending, then you know nobody is sending, and then you can send. So if you wait until the channel is free. When the channel is free, you send. You wait for an acknowledgement or a timeout. If you receive an acknowledgement, then it's a success. Otherwise, same as Aloha, you think there might still be something wrong. You will time out, and you will wait a random time and do it again. So that is the addition. It's called CSMA, Carrier Sense Multiple Access. Multiple access means it's an exclusion protocol, and carrier sense means the carrier means the channel, and carrier sense means we listen to the channel to see what happens. So imagine you're designing this protocol in the 70s, and what can we say about collisions? Is it true that they cannot occur, or can they still occur? That's the question on Speak Up now. I close the poll in a few seconds. Closing. You should see the answer and see that the majority says C, which is the correct answer. We would love to say no, but there is this thing called the propagation time, which is non-zero, that we saw 2 weeks ago. Here is a time and space diagram. Now, time is flowing vertically and space is horizontal. This is what happens when A sends a packet. So the vertical distance here is the transmission time. If that's at that time, Ethernet was 10 megabits per second. So you can compute this time here from the 10 megabits per second. And then the signal propagates on the wire, and the propagation here is shown by the non-zero propagation time is shown by the fact that there is a slope. It's not a rectangle, it's a parallelogram. So it takes some time for the signal to come to the other end here. So it is quite possible that A is sending, and when B listens, well, B hears nothing because A is already sending, but by the time the signal from A will reach B, B has already started sending because things are not instantaneous. So there will be a failure, and this failure will be visible here. The places on the cable where those two shadows intersect means there is a collision. This is a place where you have the two signals that are superimposed on the cable here. So if you're in this region here, you will see a collision here. So it is not true that that entirely eliminates collisions. Collisions are still possible here. Right? So CSMA avoids some collisions, but not all. So it's much better than ALOA because the period of time during which a collision is possible is given by the maximum propagation time. Since the cable is short, the maximum propagation time is also very short. But because of that, we still need to do not just CSMA, but also we need to handle collision. There's zillions of ways to do it. The traditional Ethernet does it with this simple code here that is called CD, collision detection. You simply send, like we said before, so I listen to the channel. When the channel is free, I send, and I wait. And while I'm sending, I'm also listening, and I wait to see whether, while I am sending, I also hear that someone else is sending by comparing the signal I'm generating to what I hear. If they are not significant, if there's a significant difference, it means I had detected a collision. By detecting a collision, then I stop sending and I send again after a random time. And here you have more details of how the random time is chosen. Otherwise, I'm successful and I continue. Now, we see there is an additional little trick. We wait for an interframe delay. That means after sending, we don't immediately send. This is for two reasons. First, to give a chance to other systems to seize the channel by seeing an empty channel. There's also other physical layer reasons, is because on Ethernet, classical Ethernet, you have what is called a non-synchronized physical layer. The problem is when you send data, let's say at 1 gigabit per second, that means that within 1 second you send 1 gigabit, or within 1 millisecond you send 1 megabit, right? Now, when you send data to another system, this system receives this megabit, but how do you receive? You need to sample the channel using your clock. Right? So there's the clock of the receiver and the clock of the sender. The two clocks are quasi the same, but not exactly. Accuracy of clock depends on the type of crystal you have, but the cheap clock has a relative accuracy of 10 to the minus 4. That means by this time one clock sends 10 to the ticks 10 to the 1004 times, the other clock might be off by 1 tick, which means when we say 1 gigabit per second, there is an inaccuracy about that. It's 1 gigabit per second plus or minus 0.01% of this value, because the clock of the system that is sending at 1 gigabit per second is not exactly 1 gigabit per second. It's 1 gigabit per second of this clock, but the seconds of these clocks are not the same seconds of another clock. Of course, for us human beings, those things are hardly visible, although if you have a free running watch, you will visibly see that at the end of the day, it is off by a few seconds, because there are so many seconds in a day. If you have an accuracy of 10 to the minus 4, that gives a visible number of seconds. So your watch, if it's free running, at the end of the day, it's if it was accurate this morning, tomorrow morning, it will not be accurate. At the time scale of packets, the same thing happens. How is this problem solved? There are different ways to do it. There are two approaches, synchronous or asynchronous. The simplest, which is the one used by practically all systems except industrial computers, it is asynchronous. That means when I send a packet, I use my clock. The receiver will use a trick called a phase lock loop, which is a way to derive a local clock from the signal that is sent. All signals, physical layer, will use invariably sines and cosines because we know how to do things only with those types of signals. So when you have sines and cosines, by analyzing the shape of the signal, you see the clock of the sender. Right? So you retrieve this clock with a specific feedback system, and you use that clock to read the signal that you receive so that you will not skip one bit after 10,000 bits. Right? You use that clock and you put the packet that you received in a buffer. Right? So far the problem is solved, but almost, because if the guy who's sending me at 1 gigabit per second has a clock that's a bit faster than me, then it sends a bit more. After 10,000 seconds, it has sent 1 second more of packets. So my buffer will overflow. If there's a constant stream of communication from A to B, there's a problem if A is slightly faster than B. So what we do is between any two packets, we introduce some idle time so that I stop for a number of bits, or I don't stop, I send what is called in Ethernet preamble bits that are here used to make, for example, if your clock is slightly slower, you can skip a few of those bits because they're not part of the data. They are just either called preamble bits or jamming bits. So those are the reasons for that. They are truly physical layer reasons, so not really the focus of this course. And this is how these things, when put together, will work. So here I'm assuming back to our space-time diagram that we had before. A is sending data to B. A starts to send. And by the time the message reaches B, B was also sensing, and B is happy since the channel is idle. Therefore, I start transmitting. But immediately, here it's instantaneous, but probably so that's the beginning. And a collision is created because we were in the vulnerable period. So what B will do is it will, to reliably detect a collision, you need to transmit for more than 1 bit of time. So you enforce that the collision is long enough so that everyone, including B, can detect it. Those are called the jamming bits. But again, those are small details of the physical layer that we could ignore. And now the collision is detected by B. And then B, having detected a collision, uses the back-off algorithm, does a random timeout, and will retransmit later. And because now this time is with high probability not causing again a collision at A, there will be the same thing at A. A also senses the collision at this time and computes another random time, which in this case T1 is larger than T2. Of course, the difference between two random times is always larger than the round-trip propagation time. Right? If T1 and T2 were very close apart, we could have the same problem. But this is always a multiple of a quantity that is at least as large as the round-trip propagation time. So by bad luck, they could have picked the same, and then there would be a second collision. But there's a high probability that they won't. Here, T2 is smaller than T1. B wins, transmits. And now when the timer of A expires, then the channel is busy, and so A will wait until the channel becomes idle and will therefore have given the way to B. This is how, in this simple case, the collision is resolved. There are a few changes that you've noticed compared to the Aloha and CSMA protocols. Here, there is no acknowledgement because we believe that the collision is detected because the medium is transitive. So we save an acknowledgement. That was a small saving. We'll see that Wi-Fi still has acknowledgement because Wi-Fi cannot make this assumption. But the consequence of saving the acknowledgement is that if we are in this scenario here, there might be a problem. Here we are in a scenario where the frame transmission time is short compared to the propagation time. The propagation time is the time from the first bit of A to reach B. And we see that A has completely transmitted its packet before a colliding packet of B is received at A. So in a case like this, A will not see a collision. A will see, I've done my job, I've sent my packet, the channel was idle. Then I've received a packet from B here. If there is no echo of the signal at the end of the line, you achieve that by putting a resistance that matches the impedance of the cable, the packet of A will not come back. So it will be truly like this. A does not see a collision. But that might be a problem because if the packets of A and B were intended to C, for example, C can see a collision. So you cannot guarantee in this case that the packet was truly received by the intended recipient. Of course, in such a system, you don't know where the recipient is. This problem will be avoided if the time to transmit a packet is at least always as long as the round trip time here. Which means that we must ensure that in this protocol, in Ethernet, this is ensured by making sure that we match the minimum packet size, the bit rate at which we send, and the maximum size of the network. For example, at 10 megabits per second, the network diameter, I said 1 kilometer, it was wrong, it was 2 kilometers. The minimum packet size is 64 bytes. So if you have a packet smaller than 64 bytes to send, now with IPv6 and TCP, fortunately, we're always at least close to, and Ethernet, we are above 64 bytes. But if you use industrial protocols that are highly specialized and have very short headers, that might be the case. So then you add padding bits. You make the packet extra longer. And in Ethernet, there is a field that says what is the length of the packet. So the length of the packet will indicate the length of the packet, of the useful bits of the packet, excluding the padding. So if you make the transmission time always larger than the round trip propagation time, then you will never be in the left case, you will always be in the right case. This is why on Ethernet, at least historical Ethernet, there is a minimum packet size. So what I describe is really for museum. You can see in the Bolo Museum, that kind of things. That was for historical Ethernet. And also AppleTalk. AppleTalk, when you connected Macintoshes together, it was exactly the same thing. The details were not all exactly the same, but it was a variant of what I've described here. And it was truly connected by, here, those are the T connectors I mentioned. It was truly a pure, so the logic was in the computer, in the Ethernet adapter, and the network is just only a cable. This is also called half duplex Ethernet. That's a terminology you will sometimes see. Duplex means you can talk in both directions at the same time. And half duplex means you can, but not at the same time. So an Ethernet cable allows communication from left to right and vice versa, but not at the same time. So it is truly a half duplex. It's more than half duplex. It allows one out of n to speak at the same time, but it's called half duplex. And this half duplexing is made with the CSMA-CD protocol. Wi-Fi is similar. So Wi-Fi uses all the ideas of CSMA-CD with a little variant where in Wi-Fi you cannot assume necessarily that C, as shown here, can hear when A is speaking, because the base station might be in the middle. Perhaps the power sent by A is less than the power used by the base station. The base station is typically connected to main supply, power supply, the mobile device not. So the B might send with more power than A, and A might send with just enough power to be heard by B, but not by C. That's what is called the hidden terminal problem of Wi-Fi. This is solved by using the RTS-CTS data exchange. An RTS means ready to send, CTS means clear to send. That's a very, very short packet, which is not a true packet, it's just overhead, it's just header. And if A wants to send data to someone, first we send to the base station in that case. So A always sends the packet from the MAC layer viewpoint to B here. And before sending a packet to B, A will send a very short ready to send message. And the trick is that B will say, yes, I'm ready to send because I don't hear, I sense the carrier and I see no one else is sending. But this clear to send reply will be broadcast to everyone. And therefore, if C is also wanting to send something, C will hear this clear to send. And whenever C hears a clear to send, it stays silent for some time. It will deduce that somebody is transmitting. and it will back off as if there would be a collision. Of course, there can still be a collision. C could have sent a packet to B at the same time, but this collision will be only on the ready-to-send signal, not on the entire packets, and those packets are very small, so that would that reduces the time during which a collision is possible. But a collision is possible, so there are collisions on Wi-Fi, like there are on Ethernet or on ALOA. The ALOA we saw can be used up to 18%. Ethernet can be used, CSMA-CD, the maximum utilization is much larger, depending on properties of the network. It's above 90%. Question? The clear to send is broadcast. The clear to send is broadcast to everyone. It contains the acknowledgement of the message that was sent by A. So when A receives it, it understands that's for me, I can send. And all the others understand it's not for me, and therefore I should back off. The other difference with Ethernet is that there is an acknowledgement that is sent. So only if all of this succeeds, the transmission will be considered successful. Otherwise, it will back off if the CTS is not received, for example, or what is a very frequent case, if A was trying to send and here's a CTS that is not for A, then it will conclude that there was a collision and will back off and transmit again. CSMA is very complicated. The Wi-Fi is very complicated. The IEEE standard is close to 3,000 pages. So there are zillions of different optimizations that are done. We will cover one or two others in a few more minutes here. There are variants that are possible, but that's the basic stuff. So essentially, that's good as long as the thing is very local. So if you would do Wi-Fi over a very large area, then the bandwidth delay product can become large, and the amount of time spent in collisions and handling them could become very large. So Wi-Fi is typically, as you know, local area in this room, for example. Wi-Fi can be used also very long distances with directional antennas, but then you typically assume that you would have only a point-to-point link. So you have only one source and one destination, so that this clear to send and receive to and ready to send will essentially not result in collisions here. Assume we are in this network and we have several nodes that want to transmit. How many do you think is it possible to transmit in parallel? In parallel means concurrently at the same time. I close the poll in a few seconds. Closing. And the majority says A, which is the correct answer, at least with the version of Wi-Fi that I've described. There are many optimizations of Wi-Fi that are being discussed. There's Wi-Fi version 6, there's version 7, etc. But here with the version that I've explained, it's the same channel that is used for the communication. There's a unique channel. So when the base station talks, it's the same channel as when we talk to the base station. In fact, Wi-Fi is peer-to-peer in principle, can be used peer-to-peer in principle. That means there's only one frame in total that can be sent at any point in time. If you have a 1 gigabit per second Wi-Fi with 1,000 users, well, at any point in time, only one frame can be sent. So you're sharing the 1 gigabit per second between 1,000 users. That's the what is given by that. In reality, you have less because, as we've seen, there are collisions that will make you lose a few percent of the available bit rate. Voila, we close here for this first part. We do a break. And after the break, we will see what is the reality of today's Ethernet and such networks. What we saw in the past hour is relevant for Wi-Fi, power line communication, but not at all anymore to Ethernet. So that's historical Ethernet. So the very first Ethernet, the way I said here, turned out to be a very bad idea. It was fantastic in universities and so on, but the industry never took it over because cabling everything over a common cable is quickly a nightmare. Why? Well, because of if there is any fault in the cable, it's very difficult to locate where the fault is. So imagine you put the same cable for that crosses the campus, and that's the way it was at the beginning. Then if there is, for example, construction somewhere in an office, and you damage the cable a bit, if you cut it, then it will be easy to see that it's cut. But if you damage it a bit, perhaps the cable is no longer transitive. There's propagation problem here, and detecting where it is, because everything on the cable is analog, requires analog devices. You have to go into the cable with analyzers and oscilloscopes and that way. So it's okay for CERN, high energy physics, that kind of environment. But for businesses that just want to do business, that's office work, that doesn't work. So what people that had no success on the market, instead token ring, which had intelligent cabling systems that were easy to monitor when there's a fault, were very successful for some period of time. And then people quickly realized, but by the way, and the technology evolved very quickly to say, instead of having this passive cabling, the solution that was required for practical reasons would be to make active cabling. So you could solve the problem by, instead of putting this T connector, you put some electronic that does the same job, but in an electronic way. The difference is that if it's electronic, you can remotely control it. And you could, for example, disconnect part of the network to see if to, for example, do fault localization and so on. But then you realize that if you start doing that thing, you might as well do something else that is much more powerful, which is the one here. If the cable that go from any system to the walls, for example, have to go through a box where there is some electronic, you might as well put what is called a switch there. You could put a system that is a queuing system where the packets that come from A, instead of being repeated with CSMA and all that stuff, you simply put them in a queue. Then the processor processes all the queues and takes, for example, round robin, takes the first available packet and sends it out on the wires in the reverse direction. If you do this, the only thing you need to manage is the two directions of the cable. Right? So you need to manage the only potential conflict is when A sends to the switch and the switch sends to A. So we could solve it with CSMA CD, and that was a possibility that existed. But also, since this kind of collision is minimal, it's only collisions between the two directions of a cable. So one way to do it is to put two cables, one for every direction, which is a bit clumsy to do with coaxial cable, but it's very easy to do with standard cable, the cable we used to do today, which are twisted pairs. So that's an example of a twisted pair. You have two pairs of wires. One pair is used for communication in one direction. Another pair is used for communication in the other direction. If you have that, you have no collision. You have what is called full duplex Ethernet, and you don't have CSMA CD. We continue to call it Ethernet, but it has nothing to do with what I showed an hour ago. Twisted pair, and that's today's Ethernet. Right? Now there are many variants of that. A twisted pair replaces the coaxial cable. Why do we have a coaxial cable? Well, because any cable is at the same time an antenna. It emits radiation, and as you know, perhaps from the laws of antennas, everything is symmetric. If you emit, you receive, and there's the same antenna for receiving and for emitting. So when a cable has a signal on it, this signal radiates everywhere, and it goes into other cables that also radiate, but also receive the signal of other cables. So there is cross-cable interference. That's the problem of cabling. You can solve the problem by putting a shield around the table, because you know from the principle of the laws of Faraday's and so on, Faraday cage, you know that if you have a conductor that is a closed surface, the electromagnetic signals cannot cross a closed surface. So when you have a cable, you put a shield around it, the signal of this cable cannot get out, and the signal from the outside cannot get in. Yes, that's why we put coax here. But coax is expensive and complicated, so we typically do what is called twisted pair. Twisted pair means the two wires are twisted, right? Twisted like this. And when you twist them, that means that from one twist to the next twist, the orientation is different. So the radiated signal goes in one direction and in the opposite direction at the next lobe, so that they largely cancel. And same thing for receiving. You receive a signal on a loop, but that goes in one direction. Now, a few centimeters later, there's another loop going in the other direction where you receive the same signal, but with an opposite sign, and then they will largely cancel. So it's less efficient than shielding, but it does a good job. And today you do both. Typically, you have a light shield around and twisted pair inside. So end of the cabling story, but that explains how things are. People quickly realized that they could replace the 2-kilometer long coaxial cable by cable that needs to go only from a computer to the next cabling box. And that probably is not 2 kilometers, although you can still do it 2 kilometers if you want to cable Ethernet and you own a place that is long, you can pull this very long cable. Or you can use shielded twisted pairs that typically will not allow you to be as long, but can be as long as 100 meters. And you have what is today Ethernet. And therefore, today Ethernet is really made on switches, which we also call bridges. They are bridges because their job is to receive a MAC frame, an Ethernet frame, and forward it to the appropriate destination. So what I was explaining is the move from a concentrator, which was simply a smart way of doing the connection. It can be a dumb way with simply the T connectors I mentioned. It can be a smart way with electronic. That was replaced by a bridge, which is a switch. And when doing that, the requirement that bridges are transparent. Transparent means what? Means that if I do the left or the right, there should be no difference in the end system. So whether I'm directly connected over a coaxial cable to 20 other machines, or I'm connected over a twisted pair to a box that does the switching, from the Ethernet protocol, from the frame format, from the fields that are in the header, there should be no difference. And if you do a Wireshark, you capture all the frames here or there, you should see no difference. You might still see a difference because the switch is probably speaking and broadcasting once in a while a few things to discover whether there's another switch around. But from the viewpoint of A sending to B, there should be no difference. In particular, that means when I send a packet to B, I send it to the MAC address of B and not to the MAC address of the bridge. This we've seen already. How do the bridges work? Well, like routers, they have tables. But those tables are about MAC addresses, and MAC addresses are not structured. They are just the serial number of the Ethernet adapter. So a bridge, for example, here, this bridge has a table that says destination A, so that the MAC address of A is reachable over my port number 1, B is over port number 2, C is over port number 3. Of course, that's a small network with only three devices. Bridge networks are typically small, but in the past there were up to a few thousand devices. So this table is as long as there are potential devices in the network. And you need to do an exact match, as opposed to longest prefix match done by IP. Here we do an exact match because those MAC addresses have no meaning. Right? In fact, if I change my computer because I bought a new Mac, I will have another MAC address, perhaps the same IP address, but a new Mac, so this will change, but I will still be at the same place here. So when a packet comes to a bridge here, you need to go to the table, search the entire table, and find an exact match, which of course is not scalable, but works well for up to a few thousands. Now, so the exact algorithm for a bridge is a bridge has several Ethernet interfaces. It receives everything. So listen, that means decode all the signals, put them on the input buffer, and then for each of the packets that are received, read the destination MAC address, and from the table, if it exists, send to the corresponding interface. Of course, if the destination is on the same as the origin, you discard the frame. There's no need sending to A, something that is coming from A. If the destination is not in the table, the bridge will broadcast to all interfaces. So we'll see that bridges once in a while will do a broadcast. But of course, this is not smart. In addition, a bridge learns the address by observing traffic. So when A sends a packet to B for the first time, the bridge doesn't know where B is. So the bridge will send it to port 2 and to port 3. It will broadcast it to all interfaces, except, of course, the interface it comes from. And if that's the only thing that happens, for example, if A sends packet to B and B never replies to A, it's bad. There will be always that type of broadcast. There's quasi no application that does that. Typically, if A sends to B, B sooner or later will reply to A. For example, if you're using TCP, there will be acknowledgements that go back. If you're not using TCP, probably you still want A is asking something to B and expects to get an answer. Or if it's not using TCP, it might still have its own application layer reliability and ask for a confirmation from B. Question, yes? Yeah. Correct. That's true. When I say it's the same, that's from the viewpoint of this of the communicating parties. So when A communicates with B, whether they're connected to a concentrator or a bridge, they do exactly the same thing. They don't need to be aware. But of course, if you do traffic analysis, you will see differences. And you're pointing to the essential difference. And the reason to do switches rather than concentrators is exactly that one. It's more efficient to send the packet from A to B, exactly, rather than to broadcast it to everyone. Of course, this is more efficient, and this will happen. So you're right, there is a difference. But how does the bridge know that B is on interface number 2? Well, the assumption is that B will reply sooner or later, and the bridge learns everything. So a MAC packet contains a source and destination address. When B speaks for the first time, then by reading the source MAC address, the bridge will discover that on interface number 2, there is a system that has the MAC address B, and it will put it in its table. In the past, for example, in Geneva Airport, there was one application that does not have this property. It was an application for displaying on the display panels for the arrival and departure times. And 15 years ago, it was using a simple system that would simply broadcast every second a packet containing the information. And this was broadcast and rebroadcast. And for a protocol like this, it makes sense to not use TCP and even not use an acknowledgement, because if this packet is corrupted, then there will be a bit garble on the screen. But a second later, there will be another packet that contains the correct information. So instead of repeating, it's better to do that. So low-speed systems use that at that frame. For such systems, the transparent bridges would simply broadcast to everyone. But that was also the semantic of the application, and they were using token ring bridges, so not the transparent bridges. So that is the principle. So the effect of that is if you buy at Migros what is called, probably not called a bridge, but multi-port Ethernet, an Ethernet multiplier or something like this, you can connect your 3 PCs here. They will connect to 3 different ports on your little switch. And then as soon as one of the PCs speaks, then the switch will learn and put it in its table, and then they can communicate with each other. That works for unicast. Multicast, we'll talk about it a bit later. Now, of course, this is assuming there's a single bridge. But if you have a network that was 2 kilometers long with the Ethernet cable, you replace it by bridges. Perhaps you have several bridges that you want to connect together. Question? Why does the bridge, this one here, Well, what you should do, if you receive a packet on interface 1, where the MAC destination address, or here, in the example I give, this should never happen. So that's a line of code that is never exercised, which is bad. If you put a line of code somewhere and you think it will be never exercised, you should wonder why this line of code is present. The reason is that a bridge can be used with a true shared medium Ethernet. You could here have a bridge that has a coaxial interface. And on this interface, there is not one device like A, but 10 devices that are connected via coax cable. Or it's connected to another bridge. So there could be a number of systems that are here. And from the bridge viewpoint, they're all on interface number 1. So if there's A and A prime that are coming to the bridge on interface number 1, the bridge receives the packet. It will look at the destination. If the destination is A prime and the destination is also on interface number 1, the bridge will assume that A prime has received it directly. Okay. Which is perhaps related to this question here. So question now is precisely what happens if I want to connect more than one bridges. I'm showing here exactly the case before, where assume we're at bridge 1 and we connect the bridge to another bridge so that effectively on port 2 there is E, C, and D, which is exactly something that could happen. What do you think will happen? Will this thing work? I close the poll in a few seconds. Closing. Closed. The majority says A, which is correct for this specific topology, but might not always work. So let's see why. It works for this one, but it might not always work. For example, if there is a link from B1 to B2, a direct link, and the topology has a loop, then it's less clear what it means to be, I mean, do we consider that C and D are on port 4 or on port 2? Perhaps yes, because it's shortest path than this one, but perhaps also this link is very short here, and this bridge is very fast, so it's not clear. In fact, if there are loops and you have this method of learning, so when you don't know, you broadcast. So when you broadcast, for example, when A sends a packet, B doesn't know where to send it, it will broadcast it. Well, it's very random what will come first. So what will come first at B2? Is it the copy sent by A by B1 via this way, or the one that goes via the lower part? It depends on how the queue was here. If there was a queue already, a packet in the queue that was waiting to be transmitted, perhaps this is the first packet that comes, but perhaps also the other one. So there is some inconsistency that could be fixed, but certainly not by the simple learning mechanism that we've seen. In fact, the way to solve it is to have what is called open shortest path computation of shortest paths, which is typically not done in that type of bridges. Also, there's another problem when B1, when a bridge doesn't know what to do, the solution is to broadcast. Now, of course, if there is loops, then the broadcast will create problems because the packets will come back. Those problems can be handled, but you need to do something else. You cannot just do the things we did before. So what is the solution that is done in networks of bridges? Well, it is the simplest of all that you can imagine. we forbid this from happening by forbidding active loops in the topology. And this is called the spanning tree protocol. So when you connect bridges together, the bridges will talk to each other such that at the end, they will decide not to use some links. For example, on this topology here, those two links here, bridges 7 and 22, will agree not to use that direct link, and bridges 9 and 2 will agree not to use that direct link. You could say that is stupid. I mean, why do you put all those links and you don't use them? And it is stupid, it is true. This is why there are other bridging technologies that we'll talk a bit later when we talk about OSPF that are inspired from the routing protocols. But that's very simple. And the idea is that local area networks typically don't have congestion problem, but the main problem that you have in local area network is loss of connectivity. You can lose a cable or you can lose a bridge. So of course, when we say 2 and 9 agree to not use it, of course, they will keep monitoring whether the other paths work. And if the rest doesn't work, if, for example, a link is broken somewhere else, they will reconsider the decision. So the loops that exist are backup, can be used as backup, but they cannot be used in load sharing, which is not the most efficient way of using things, but this is how it is done. So that was the what. The how is exactly this one. This is a poem that was written by Mrs. Radia Perlman, who is also the inventor of this protocol. So she explains very well how it is done. So the goal is to create a tree out of an active topology that is a tree. A tree for a bidirectional graph means the same as a graph that has no loop, has no cyclic cycles. There are millions of ways of building a tree, and this is not the most efficient way. You would need here to build what is a spanning tree, so the tree of minimum weight, for example. This is not what is done. First, it's based on two parts. First, we elect among all the roots one special root, the center, which is called the root. This election is done by a gossiping protocol. Essentially, when a bridge boots, it says to everyone, I am this bridge. And the bridge ID is typically its MAC address, its largest MAC address. You can also configure it if you want to configure it so that there's a higher chance that it becomes that becomes elected. And then the bridges, they simply elect whoever has the smallest identifier. So if you do nothing, if you buy several bridges from Migros and connect them together, it's completely random who will be the root. If you want to configure them and then you have a managed bridge network, which is in enterprise networks, then you configure those IDs such that the one that is at the center, perhaps of your topology, becomes really the root. So the root is elected by gossiping, and then least cost paths from root are traced. In fact, that means we compute shortest paths from every bridge computes using a distributed algorithm that we will see in detail when we speak about distance vector routing. It's called the Bellman-Ford algorithm. By talking only to the immediate neighbors, you are able to compute the shortest path to the root here. And if you want to sing this beautiful poem, you can go to the link that I give here. So this is more details about what I said. So in addition, so this results in a tree being built, because if you select only one single shortest path to a given destination, that will automatically make a tree. But of course, all bridges monitor that tree by having the root send every few seconds a beacon packet to all bridges along the active tree. And bridges monitor this if after 2 or 3 consecutive intervals they have not received the packet from the root, they will declare that the root is no longer reachable, and they will restart this election algorithm. There are other variants. We will see that the Bellman-Ford algorithm, if the root is still reachable, but the shortest path is not active, they will be able to compute immediately another shortest path. We will come back to the details of this algorithm because the same, it's a variant of the one that is used in distance vector routing. Right now, if we want just to see the effect of the protocol rather than how it works, Let's analyze the network that is given here. While doing this, there is a concept of shortest path. So we need to give a concept to what is the cost of a path or the distance. This is done either by configuration, but we want bridges to be plug and play, so we don't want to configure them. So there are default rules. A bridge knows what is the cost of a link by simply giving high cost to links that are of lower speed. So if you have a 10 gigabit per second link, it will be given a cost that is much smaller than if you have a 100 megabit per second link. Here is on this example, you have all costs of 100, perhaps because there are 10 megabit per second lines, and there is a cost of 1 because this is a 10 gigabit per second line between B1 and B3. And I'm asking you, imagine you are connecting your 6 bridges in this way. Among the links that exit B4, what are the ones that will be on the spanning tree? B4, B5, B4, B3, both or none of them? I close the poll in a few seconds. Closing. And the majority says B, which is the correct answer. Let's see more details to understand why. First, we need to know which bridge will be the route. That's essential to know where the spanning tree will be. If I assume the identifiers are literally what is written here, the smallest identifier, if we interpret that as whatever letters or hexadecimal digits, the best one is B1. So that's the route. All the bridges will sooner or later agree, because by gossiping, by broadcasting the information to everyone, they will know there is somebody called B1. At the beginning, everybody believes this bridge is the route and will say, I am the route to everyone. So B5 will say that, for example. But sooner or later, B5 will hear from B1, there is, oh, B1 is better than me, therefore I yield to B1. B1 is the root. And in a relatively short time, everybody will agree. And then everybody will work with Bellman-Ford to compute the shortest path to B1. Now, from B4, the shortest path is here, because this link is shorter. And this is not on the shortest path. So the red links are the ones that are used. And B4 and B5, as a result of that, will agree not to use this link here. So that is the spanning tree that will be computed in this network. Of course, if for whatever reason the link here B3, B4 breaks, for example, because we destroy the cable, then B4 will stop receiving the beacons from B1, because B1 beacons on the spanning tree, and will restart its computation and will establish the link via B5. Yes? So the question is, depending on the topology of the network, it might be better to use one or another bridge as a route. And exactly, this is completely true. And you do that by changing the identifiers of the bridges. So the bridge identifier contains something that comes from the box, but it also has a part, which is a priority field, which you can manipulate to give it a lower value. You do that in managed networks. You don't do that if you just want to connect a few devices in a plug-and-play fashion. And on this network of bridges, so a very frequent topology is a ring. A bidirectional ring is very frequently found in lots of networks. Why? Well, because it's simple. You number things from 1 to n, and if you are able to compute modulo n, then you can find easily who are the neighbors, where are the links, and etc. And it is among the simplest topologies that have redundancy. You still have at least 2 paths from any node to every node by going in one or the other direction of the ring here. So that is a very, very frequent topology, more frequent than this one, for example. It has some redundancy, but not for all. So the ring and rings of rings are, I would say, the vast majorities of topologies in networks that are being deployed here. Now, what will the spanning tree produce if this is a ring of 4 bridges? Well, the truth is we don't know, but some nodes will be picked as root, and then one of the links will be broken. For example, here, this link. Now it depends if there are equal costs here. For example, this link might have been broken. There is a tie here, and the protocol, the spanning tree protocol, has a way to resolve tie. It will pick always exactly one shortest path, which is very different from routing. We'll see that routing protocols typically insist on having multiple paths if there are paths of equal cost, because that improves the reliability of the network. Bridges have a different goal. They want to eliminate loops, so we pick exactly one shortest path. And if this was the one that is picked, then this link will be disabled here. Which of course means if there's traffic from A to B, it will go along the long way of the ring. You break a ring to make it a line, effectively, when you have a ring. That's an inefficiency of shortest path bridging, and this is not what routing will do. I skipped some of the slides. So today's Ethernet is really made on bridges and spanning tree protocol. There are more subtleties on the spanning tree protocol. There is what is called the rapid spanning tree protocol. There are also which addresses issues such as when we've seen that the bridges learn addresses, but we've seen also that bridges might change their topology when they detect that a link is broken or a new bridge is added. So first you must synchronize the learning with that. If you've learned that A is on port 1, and in the meantime you've changed the spanning tree, then perhaps A is no longer on port 1. So there are side effects between the spanning tree protocol and the learning here. So there is a number of other things that make the story a bit more complicated, but the basic ideas are very simple. As you can imagine, as soon as the spanning tree has changed the state of a link, more exactly the state of a port, then all the learning phase is disabled. So everything you had learned on this port is flushed, and you start relearning. In fact, if a state of a port has changed, you'd suspect the spanning tree, because it's fully distributed, might take some time to converge. So you might decide to learn not immediately, but wait a little bit to avoid loops in the forwarding of packets. Question? Is the broken link detection part of the Ethernet layer? It is part of the protocol that bridges do, which is part of the Ethernet layer. It is the bridging protocol. It is the spanning tree protocol, which uses only MAC packets. So there's no IP header, nothing here. So if you do a Wireshark between bridges, you will see what are called BPDU, bridge PDUs, bridge packets, which are Ethernet frames, but are intended to the use of bridges only for maintaining the spanning tree in particular. We mentioned Ethernet frame several times. Here is one of the 2 standard Ethernet frame format, the most common one, but not the only one that is used. The Ethernet frame contains destination address and source address, which are MAC addresses. We've mentioned them already. There are 6 bytes. It contains also a preamble and a special pattern that's related to what we discussed an hour ago about the asynchronous nature of physical layer transmission of Ethernet frames. So when an Ethernet frame starts, we send the preamble because we're never sure exactly, because we're not synchronized. We don't know when a frame may start. And this preamble contains essentially garbage, but it finishes in a well-known pattern. So when an Ethernet adapter sees that there is some power on the line, it will look with, it will try to match this pattern. As soon as it has matched this pattern, so the print should not contain this pattern. As soon as it has matched it, it knows a frame can start. So that serves the two purposes: disconnect the clock of the two systems, so make sure there is some buffer time here, and also do not require a time-slotted mechanism. When a packet starts, is detected automatically. And this is not visible. This is eliminated by the Ethernet adapter. When we do Wireshark, we don't see the preambles. We see the destination address, the source address, and then there's only one useful packet. So you see the Ethernet header is minimalist. It contains a type which indicates the nature of the packet that is contained here. The type of the packet is, for example, an IPv4 packet. We've seen that ARP used with IPv4 does not use IP packets, so that's a special type for Ethernet, and IPv6 also. And then almost 100 different packets that are very specific, but most of the time we will never see, but they all exist. For example, there is a special type for the precision time protocol that is used for high precision clock distribution between industrial Ethernet switches. There is also a different type if we use an encryption layer, MACsec, and we'll say a few words about it. So that means after that, there will be an additional header and an additional trailer that is used for authenticating and encrypting the frame. Notice that IPv4 and IPv6 are considered two different Ethernet types, which is a bit weird. IPv6 should be the next version of IP, so it should be an IP packet, but no, that's a decision that they are considered different protocol types. And at the end, there is a checksum called frame check sequence that is explained here. That's an error detection mechanism. So on Ethernet, errors are very rare, but they are not. We can even improve the performance by detecting occasional bit errors. So that's a polynomial error detection code that can correct a few bit errors. And if you receive a wrong signal that you're unable to correct, then the frame is simply discarded. That will happen once in a while, but on Ethernet, that's a very rare event. This frame check sequence is also not visible when we do Wireshark. It's removed. The adapter verifies when it receives a frame. It verifies the CRC. If the CRC is correct, the frame is correct and is delivered. But we don't deliver the CRC. We don't see it. We've seen that the MAC addresses are used for identifying destination. And this is root. We can understand now why it is in this way, because originally this was for a truly shared medium cable. So on a shared medium cable, the only way a device could receive it is by recognizing in the destination MAC address its own value here. Which of course is very unsafe, unsecure, because of course for attackers, it's very easy to spy on traffic here. This is used by bridges in the way we've seen before, using the learning and broadcasting feature of the spanning tree protocol. If the destination address is known, then we send it over the port that is in our table. If it is not known, we broadcast it over the spanning tree. That is what the bridge will do. And with a bridge, as you have rightfully observed, there's a difference with this case here, that with a bridge, in principle, only the legitimate destination will see the packet. So a bridge is more secure than a shared medium here. If you do a Wireshark, you will see that you display sometimes when we see addresses, you will see sometimes it will say Cisco or Apple or Sun Microsystem, etc. This is because the numbering of serial numbers of adapters, MAC addresses, has a prefix which is allocated to companies. For example, Cisco 000C. This block is allocated to Cisco. So this is why Wireshark can know what adapter means here. But again, those addresses have no meaning. I mean, you can change, you can buy a new Mac. The old Mac had an Intel communication adapter. The new one has a Marvell or Cisco, and it has nothing to do with who you are and where you are. We've seen that MAC uses broadcast address. Now we can understand why. It was quite natural at the beginning when the Ethernet was a shared medium thing, then broadcast was for free. In fact, if you have a true shared medium Ethernet system, the cost of sending one broadcast is the same as the cost of sending one unicast packet, because unicast is sent to everyone and filtered out at destination. This was true on truly transitive media like Ethernet cables. It's partly true on Wi-Fi. On Wi-Fi, it's true that the base station can, in fact, broadcast it to everyone, and only the intended destination receives it. But it's only partly true, because on Wi-Fi, the base station will also adapt the coding to the quality of the channel between the base station and a given receiver. If you're very close or have a very good channel line of sight to the base station, you might go 50, 100 megabit per second. If you're far behind the wall, you will go at perhaps 11 megabit per second. It will depend on the quality of the channel. And if you broadcast, then you broadcast at the lowest quality possible so that everybody receives. So there's still a cost even on broadcast medium here. But that explains why broadcast is heavily used in local area network. It comes from this reason here. So if this MAC address is used, then of course everybody will receive it. The broadcasts, of course, are not sent to everyone, but over the spanning tree. You've noticed that there is no TTL in the MAC header in the Ethernet format, which means if there is a loop, then we're really in big trouble. If there is a loop in the network of bridges, the network is down by sending a single packet. And this packet will loop forever and will occupy all the network. So that's the dream of attackers. You want to deny a service, you create a loop and you send one packet and the network is down. That happens with the MAC layer because there's no TTL. And the way this is solved is, but the spanning tree is very, very careful. I mentioned that as soon as a spanning tree reconfigures something, there are very long timers to wait until we have relearned all the MAC addresses here. There are optimizations. If you're sure that the part that has been reconfigured cannot create a loop, then you don't use those timers. This is what is called the rapid spanning tree protocol, the rapid variant of the spanning tree protocol. We won't go through these details, but you need to manage this interaction to avoid loops at all means. And in the lab, you will be able to play with those loops here. So this is for broadcast. We've seen that there are multicast addresses, and IPv6 loves multicast address, in fact, hates broadcast and avoids broadcast at all means. So IPv4 multicast address are mapped to this specific prefix, and IPv6 to that one here. And an Ethernet adapter must be configured to what we call subscribe to a MAC address. So this, if you watch a TV channel, a football match that is sent by Swisscom TV using IP multicast, then the software will instruct the Ethernet adapter to receive the traffic. You're probably doing it over IPv6 if you have a modern installation. So it will instruct it to receive all those MAC destination addresses here and the devices that don't subscribe will not receive it. You see that broadcast, at least on this shared medium Ethernet, is, multicast also comes for free. So doing broadcast, multicast, or unicast are exactly, from the network viewpoint, the same cost. It's just a different configuration of the adapter. So that seems very easy. We'll talk more about what those subscription protocols are when we talk about multicast here. We'll skip this one. And no, I will not skip this one. I will, this I have done. Well, I will come to this last topic in 1 minute, which is virtual LANs. So the reality of Ethernet today is that one. It is the virtual LAN. Okay, and virtual LAN are a fascinating topic, but we will wait 1 week to see how it works.